Quantum decoherence is the process by which quantum systems lose their quantum properties and begin to exhibit classical behavior due to interactions with their environment. To illustrate this, imagine being at a symphony orchestra with over 50 musicians, each playing a different instrument. When the concert starts, all the musicians play in perfect harmony, creating a beautiful tune. However, if a few people who are not part of the orchestra start playing their own instruments from the audience, it disrupts the original performance. Instead of harmonious music, you end up hearing a chaotic mix of sounds. This transition from harmony to noise is a useful analogy for understanding how quantum systems shift to classical behavior. In the classical world, we can explain many phenomena using the classical laws of physics. We can visually observe and understand these phenomena as we detect, observe, and analyze them in the real world. However, the quantum realm is vastly different. In the quantum world, particles can exist in multiple states and behave in ways that don't always make sense in the classical realm. For example, when you flip a coin in the real world, it will land on either heads or tails. In contrast, in the quantum world, particles can exist in a superposition of states, meaning that they can be in multiple states at once. You might be familiar with Schrödinger's cat, a thought experiment that explores the idea that a cat can be both dead and alive at the same time. This concept seems nonsensical to us in the classical world, but in quantum physics, it's a demonstration of superposition. Coherence in quantum systems refers to their ability to maintain well-defined relationships between different states. When coherence is preserved, we say that the system has a certain level of order among its possible states, which is critical for processes like quantum computing. However, quantum systems are very sensitive to environmental interactions, so they need to be isolated to preserve coherence and prevent disturbances from external factors. When a quantum system does interact with its environment, the information within the system becomes mixed with information from the environment, leading to a loss of coherence. This process, known as quantum decoherence, causes the potential for superposition to collapse, making the quantum system behave more classically. But why should we care about quantum decoherence? Maintaining coherence in quantum systems is crucial, especially for applications like quantum computing. Quantum computers depend on particles being in a superposition of states to perform complex calculations significantly faster than classical computers. However, if these particles lose their superposition due to interactions with their environment, quantum decoherence occurs, which compromises the quantum computer's ability to function as intended. We have already created a dedicated video on quantum computers linked in the description. In that video, you will see that quantum computers are vastly different and look nothing like typical laptops or desktop computers. They are large machines that require specific temperature conditions and careful isolation to prevent unwanted environmental interactions. Decoherence also sheds light on fundamental questions in quantum mechanics, such as the measurement problem and how the wave function collapses when a system is observed and measured. In summary, understanding quantum decoherence is essential for building and maintaining reliable quantum technologies, such as quantum computing and encryption. In short, in order to build reliable quantum technologies, it is imperative for researchers to understand quantum decoherence and master methods to control its effects in quantum systems.